Let's talk about the curl of an electric field now. In particular, we're going to talk about the curl of a static electric field, which is important for me to point out because later we're going to talk about the curls of non-static electric fields that are changing with time, and the curl will not be zero. But in this case, we're going to show you that the curl of a static electric field is always equal to zero. That's a special property of the electric field. Let's start by thinking about the electric field around a positive charge. And the electric field is radially outward because, again, it points in the direction that a positive charge would move within that field if it was free to move. And I'm not super good at drawing these for some reason still. Did you guys get the point? Bunch of arrows. They should all be equal in length, but they're pointing outward. Okay. So we're going to apply this to a point charge, which means we're going to try to calculate the curl of the electric field of a point charge. To do this, the first thing we want to do to conceptually think about this is we can figure out a path over which we can calculate the line integral E dot dl. Okay. In this case, if I think about E dot dl for this particular field, it has to be zero. And the reason is, if I go around this loop, E is perpendicular to dl everywhere. Okay, remember dl is just a little portion of my loop here. So it doesn't matter where I draw this little tangent portion of my loop, it's always going to be perpendicular to the purple line, which is the direction of the electric field. For this to be true, this particular relationship cannot depend on the loop. So it can't depend on the loop that we choose, the closed loop, okay? And we picked a particularly easy one in this case, obviously. So let's pick a different one. Let's just think about a couple of these field lines. Still the electric field. Now we're gonna do the same line integral, but we're gonna do it over just a portion of the field. We're not going to go around the charge anymore, but instead we'll do a line integral that looks like that. And we still want to do the same thing, so we're still going to calculate the dot product of the electric field and portions of that path, that closed path. Here, I can't just make an argument that it's going to be zero. If I look here at my closed path, I can make the same argument that it would be zero here and here, because of course the electric field is perpendicular to our dl on those two sides. But if I look at the other two sides, here I would get some positive contribution to my line integral, and here I would get some negative contribution to the line integral. And that's because in these regions, okay, the electric field is, in this case, it is parallel to our dl, and on this side, the electric field is anti-parallel to our little dl side. Okay, so let's actually figure out what that might be. Well, I just have to plug in the electric field equation for a point charge into my integral here. I'm going to pull out the constants, and I'm just going to leave what you actually have to integrate over on the inside. Okay, here, what you're left with is 1 over, and I'm not going to do the fancy R here. We're just going to put this particular point charge at the origin. So I'm just going to call it an R. dr, okay, that'll be for one side. And then the other side, same deal. dr. And the sign here really comes in when we split this line integral up into these two paths. The sign, whether it's positive or negative, comes into how we define the limits of our integral. And there's lots of examples of this in the book if you guys don't remember how to do line integrals. But in this case, if I define the points where I'm doing the line integral over as R1 and R2, for the first path there, this side, sorry, I never actually labeled these with numbers. We'll call this one 1 and this one 2. For the first path, I'm going from R2 to R1, and then the next path, the second path I've labeled there, it's going from R1 to R2. Okay, so when I rewrite this, obviously we're going to be able to flip the integration limits on that second integral. When we do that, that's going to give us a negative sign. And we can prove in that way that, again, even if we choose this path that doesn't even go around the charge, we get a line integral around this closed path that is equal to 0. And this particular relationship would be true no matter how many point charges that we superimpose, or the fields of point charges that we superimpose onto one another. We could come up with a really complicated field. Think back at that PhET charges and sims simulation where you could just pile charges all over and it would change the electric field and turn it into something really complicated. If you do that, you're still going to find around a closed loop, this integral would be 0. And the reason has to do with superposition. So I'm going to argue that this is true for any number of point charges. Okay, and that's because if I think about it, what I'm doing is I would still be taking the curl of a total electric field. That total electric field would be the result of adding together a bunch of individual electric fields of however many point charges you had. Okay, and when you do that, you can actually distribute this curl kind of like this. Let me not miss the vector sign there. You guys get the point. And each individual term here is going to be 0, so therefore the whole thing has to equal 0. Okay, and remember, even if I have an object that has some continuous charge distribution, right? When I do those integrals, what I'm doing is I'm really breaking it down to infinitesimal bits of volume or area or a little piece of a line, and I'm treating it like a point charge. Okay, so I would argue that even for those types of objects, as long as the charge on them is static, the electric field that they produce is going to have no charge. Okay, so I want you guys to recall that the work, what we call work, which to have energy is the ability to do work, but if I wanted to calculate how much work I've done, which has units, same units of energy, joules, I would take a line integral and calculate the force applied over some loop. Okay, so this is looking a lot like what we were trying to do when we were defining the curl. Okay, but if you guys remember, if the force happened to be conservative, what we called conservative, then it didn't matter what path you took. Okay. Okay, so the work done by a conservative force was independent of the path. And the example always was, right, if you take an object from A to B and it's just feeling the force of gravity along that particular path, it didn't actually matter how you moved it along that path, you'd still be doing the same amount of work. It would be changing its potential energy by the same amount. Okay, so for example, gravity is a conservative force. Okay, and again, if I took an object like this pencil and I lifted it up in the air, I'm doing work on it. And when I do work, I'm changing its potential energy. And it doesn't matter if I lift it straight up or if I lifted it up in a curly, weird, loopy direction. The only thing that really mattered, not the path that it took, but the difference between its initial height and its final height. That's what determines the work. The same thing seems to be true as long as I have a non-closed path. I just showed you if you have a closed path, then it's going to be 0. But for a non-closed path, the line integral of our electric field dotted with dl, okay, is independent of path. And one way to think about that is, again, remember the electric field is just the electric force divided by charge. And I think it makes sense to you that just like a gravitational field has this property where when you move things through it, the amount of energy that you give them is independent of path. The same would be true of an electric field. So the electric force is a conservative force. Okay, and again, if you need to remind yourself what the conservative force means, again, you could crack open your 182 or I think 182 textbook, or you could probably just Google it and find some good information online. Okay, so what that means is if I draw this picture similar to what's already in the book, okay, and I want to calculate the integral between A and B, I can choose any path I want. Okay, I can choose a nice path, I can choose a mean path, I can choose whatever path I want to in order to do that integral, but at the end of the day, it's only going to depend on the values at the endpoints. Okay, so just like for gravity, the amount of potential energy you give it only depends on the initial and final height. Here, this particular integral still only depends on values at the endpoints.